Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be revisiting Coulomb's law one more time. This time, instead of doing Coulomb's law for two charges or even for a set of individual charges all acting on a common charge, this time we actually want to do Coulomb's law but for an extended source acting on a point charge. Now, I should mention that in some sense this is kind of a non-standard lecture, even for calculus-based, in as much as typically we introduce another concept first, which is electric fields, and I'm going to sort of revisit this topic when I've introduced electric fields. Nevertheless, I did want to kind of do a quick video in which I calculate how much force would be due to a charge, how much force would act upon a charge due to an extended continuous source. And I'm going to do it without reference to electric fields, and then in a future video maybe I will revisit this in the context of electric fields. So what do we need to recall for this video? I suppose the first thing to recall is just Coulomb's law itself. So what does Coulomb's law say? First thing to recall is so Coulomb's law says that the force between 2 point charges will be given by Coulomb's constant. That's 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. So Coulomb's constant times the product of the two charges divided by the distance between the two charges. So that's the first thing to recall. The second thing to recall, and this is kind of a recall, this kind of came out of an example that I worked in a previous video, is that charges, if you have multiple charges, you can use the superposition principle to find the total force, or you can add forces together if you'd prefer to think of it as that. So we had a separate video for that, and typically what that really means is that the total force, let's say the sum of forces, could be represented by a total force, and that in turn is basically the x component times I hat plus the total for the y component times j hat, and that should be f1x I hat plus well, let's say f1x plus f2x plus f3x, etc. times I hat plus f1y plus f2y plus f3y, etc. j hat. Okay, so that's forces adding as vectors. The last thing maybe worth recalling is sort of some symmetries. And again, this is something that I didn't address directly. You know, these two came directly from previous videos. The symmetries property kind of comes indirectly, but it comes from an example. Basically, what this particular property is saying is that if you have, let's say, two charges and they're both the same distance away from the same charge, and they're both the same vertical distance away from the charge, such that this is Q1 and this is Q2, and this distance right here and this distance right here are equal. We'll just call this distance y. If Q1 equals Q2 in this case, then the sum of forces will simply be F total x I hat. And you can do a similar thing for a y hat or a j hat. This basically, you could draw from this example that I did where I had 3 point charges all in a line and then another charge somewhere over here. If you ignore charge 2 and just look at charge 1 and charge 3, when we went to add their forces together, F3qy and F1qy were equal. So if I was to write that sort of main point from all this down, F3qy and F1qy were equal forces but in opposite directions. And so they ended up canceling out when we went to add the total forces. Now, why that last point is important is because sometimes it helps save us a little bit of mathematics in doing our extended source calculations. Sometimes it doesn't, sometimes it does. So how do you deal with an extended source? Well, in some sense, this middle point here, that the sum of forces is F1 plus F2 plus F3, etc., and that's the total force, that's kind of the basis for an extended object. So let's say that I have some object like this, and it is charged. So there's charges everywhere in this, and I'm wanting to figure out how much force is going to be applied to some object over here. Well, in some sense, this little piece of it has a value dq, and I'm actually going to use a capital Q here because it's an extended object. So let's say like total charge might be q. This little piece has some force dq, or some charge dq, and it's going to apply a force df, which is equal, if I have a little point charge q here, and this distance right here is r, df will be equal to Coulomb's constant times this point charge that I'm looking at times dq over r squared. And so if I want to find the total force, F total, which I'm just going to represent as F, I'm basically doing the same operation that I did up here, but for an extended object, F should look like the integral of df. And so that ends up looking like essentially the integral of kc little q dq over r squared, and we might as well just add an r hat value in here. So that's basically how you go about doing extended object force. What does it actually mean? Where's the complicated thing here? Because if I look at this equation, it looks a lot like I should just be able to write equals kc q big Q over r squared r hat, right? So if I'm looking at this, if I have integral of a constant times another constant times a differential divided by something else that is constant with respect to that differential. So if dq doesn't depend or doesn't affect or doesn't have any really dr term, this would be easy. However, r dq is often something, some function dr, or maybe they are both convertible to something else. So this integral kc q dq over r squared r hat, generally speaking, is not going to equal kc q big Q over r squared r hat, because usually this right here is going to be some function that contains this right here. And in fact, if we go back up to our original diagram, you can see that if I picked a different dq, like one over here for example, that I'm going to have a different value not only of r, but also of r hat. So my dq kind of affects my r and r hat, or my r and r hat kind of affects my dq, and vice versa. So basically, the hard part in all this is figuring out how to get these three terms in terms of one common variable. Okay, again, the hard part, dq, r hat, and r, the r squared term is r, need to be in terms of one common variable. It may be two common variables, by the way, or three. But what you're going to find is that if it's more than one, it's more than one in such a way that both dq and, let's say, r hat will be a function of x and y. And so I may have a dx, dy, and then an x and y buried in these two things. So what does that actually look like? Well, from here, it's basically just examples. There's no one magic bullet to this beyond what I've written. Basically, you just have to figure out how can I express these in terms of a common variable. So let's work an example just to get an idea of what that may look like. So the example that I'm picking to work for this video is to consider a wire of length 16 centimeters, which is placed along the y-axis and centered on the origin. It has some uniform charge distribution, and we want to know how much force it applies to a single point charge of 2 microcoulombs, which is placed 48 centimeters away on the x-axis. So in some sense, the first thing that you should be doing with these kinds of problems is drawing a diagram for yourself. So let's draw a y-axis, which I'm going to draw right here, and let's draw an x-axis, which I'm going to put over here. So here's x, here's y. My wire of charge is basically here along these two axes, and my point charge is somewhere over here. So this right here represents Q. This right here, we could call this number right here lambda. So this has a value of lambda, and again, it's 16 centimeters long. That means that we have 8 centimeters above and 8 centimeters below the x-axis. And then this right here has a distance of 48 centimeters. Now, we want to know how much force is being applied here, so we pick for ourselves a little element of charge. I'm going to call this dq. And dq is going to be lambda times dy. The logic of this being that lambda is defined as total charge divided by total length. And so if I want to get a dq, and I'm going along the y direction, dq should look like lambda times dl, and so that looks like lambda times dy. What is the distance from this charge over to this point? So here is r. What is that distance? Well, if this distance right here represents y, then it should be clear that r squared is equal to y squared plus, and let's just call this x naught for the sake of argument, so plus x naught squared. All right, and so that is y squared plus 0.48 meters quantity squared. Now, before we do too much math with this, it's worth noting that I can also choose a little dq down here, dq. And that dq that's down here could be a distance negative y away from the origin. And it's also going to have a distance of r away from this point charge. Now, why does that matter? Well, both of these dq's are kind of acting in a manner similar to these point charges here that we talked about with the symmetries. And so what that means is that we expect the y components of these to cancel out. And so actually, I'm not looking for the y components as well as the x components. I'm actually looking for, in some sense, only the x components of the force. And so my total force, instead of having to integrate over r hat, I can now just integrate over the I hat component. So in some sense, this becomes integral of kc times dq over r squared times the I hat component, and this right here in some sense is like the x component only of this force. Okay, so what does that allow for me to sort of do here? Well, it actually simplifies the math just a little bit. What I, in some sense, now expect to have happen is my integral has simplified somewhat. So f becomes integral kc, and then instead of dq, I have lambda times dy, and over r squared becomes over x naught squared plus y squared. Now notice that we've just established with this that there's now a y down here and a dy up here. Aha! Now we have something that we can actually kind of integrate, right? So what does that do for us? Well, we notice that we don't really care about the y component of this. We care only about the x component. And so in some sense, what we can say is, let's say here's r hat. In some sense, we have f sub x should look like f times cosine of some angle. So let's come back over here and let's go ahead and define an angle theta right here. So cosine of theta, and this is this gives me the I hat component, and fy ends up being f times sine of that same angle. But this component is going to go away due to symmetry. So I have only this component left to figure out. So where does this component show up in here? Well, f as such basically represents f r hat, or in other words, integral df r hat. And so this r hat term can be represented by cosine theta I hat plus sine theta j hat. So this term is going to end up going away when we do the integration due to symmetry. And so my total force in this case, if I pull some constants out, I can pull the kc, I can pull the little q, and I can actually pull the lambda all outside. This ends up looking like the integral, and let's write in here from bottom to top, from bottom to top of dy over x naught squared plus y squared times cosine theta I hat. Now coming back over here, looking at the theta, I notice that theta, this cosine of theta would be this length right here divided by this length right here, x naught over r. Put differently, theta is also a function of y. Okay, so now you can see what I'm talking about with this hard part. dq, r hat, and r all need to be in terms of a common variable. So in some sense what we have to do is either y needs to be put in terms of theta, or theta needs to be put in terms of y. We can pick either way here. Coming back again to this slide, I notice that the tangent of theta, so let's put this over here, tangent of theta is equal to y, the opposite, divided by x naught. Alright, so what does that mean? Well, if I take a derivative of both sides of this equation, what will that get for me? By taking a derivative of both sides of the equation, I mean basically like, let's rearrange the equation and now let's figure out what dy d theta is. Okay, so that's going to be x naught, and then what's the derivative of tangent theta? You should maybe pause the video and work this one out for yourself, but I will just give you the answer for video brevity's sake. So pause it, think about how you might get the derivative of tangent of theta if you don't know it off the top of your head, and then unpause it. So if you've done that, then you know that the derivative of tangent is 1 over cosine squared of theta. One more thing to note, if I come back over here, this is theta. Again, r squared is x naught squared plus y naught squared. But if I take the cosine of theta, then that's going to be x naught over r. So coming back over here again, cosine theta is x naught over r, and that means that cosine squared of theta is equal to, and then you have x naught squared over r squared, which is x naught squared over x squared plus y squared. Or in other words, if I come back to this term that has x naught squared plus y squared in the denominator of my equation, x naught squared plus y squared just is x naught squared over cos squared theta. What does all that algebra get for us anyway? Well, for starters, let's note that this right here implies that dy is equal to x naught d theta over cosine squared theta. Okay, and so having done that, let's come back over to this equation. I have a dy term that I need to substitute out for some thetas, and then I have an r term, or an r squared term, that I'm going to need to substitute out for some thetas. So I'm basically taking these two terms and I'm going to substitute them out for thetas. So in some sense, I'm basically just doing this right here via all this math. So what does that look like? Well, f is going to be kc lambda little q integral. And now I said I would go to in sort of blue for the dy. So my dy term is this stuff up here. I have x naught d theta over cosine squared theta. Then in green I need to do my 1 over x naught squared plus y naught squared term. So let's come back over here. So I have 1 over this. So if I want to do 1 over all this, that basically means I have cosine squared theta divided by x naught squared. Okay, and then coming back over here, we still have a cosine theta I hat term that we're not substituting out. So we have cosine theta I hat. Now we probably notice here that there are some like terms, like I have cosine squared theta here, I have cosine squared theta here. I also have an x naught here and an over x naught squared here, but those ones we're maybe a little less interested in. What about the bottom and top? So bottom and top. So limits. Well, again, the symmetry argument means if I integrate from bottom to top, that this is actually just going to be equal to twice the integral from 0 to top. So this is symmetry once again. I'm just using the same exact argument that I used up here in this entire thing, because when I went to add the force from this and the force from that, I just ended up getting F3qx and F1qx are equal, and so the total force from these was just 2F1qx. So that's part and parcel of our symmetry argument. So coming back down here, what that basically means is I just need to figure out either the top or the bottom. Well, again, I have here 8 centimeters. I have 48 centimeters here. And I have theta top here. That's my top value of theta. So tangent of theta top is 8 centimeters over 48 centimeters. And that means that theta top is the inverse tangent of 8 over 48. 8 over 48 is a sixth, obviously. So we go inverse tangent of 1/6. Whoops, I did tangent of 1/6. Let's try that again. Inverse tangent of 1/6. That's 9.462 degrees. So 9.46 degrees. Okay, and now we're ready to basically do our integral. The force in this case is going to be Kc times Q times lambda. I'm also going to go ahead and pull out the x naught and the I hat part at this point, because those are not affected by this integral. Note that I've canceled an x naught on top with an x naught squared on bottom to be left with just an x naught on the bottom. We're integrating from 0 to 9.46 degrees, and what we have here is cosine theta d theta. And so what is the, well, this ends up giving us, this integral at least ends up giving us the sine of theta. So we have Kc q lambda sine theta divided by x naught I hat evaluated from theta equals 0 degrees to 9.46 degrees. So sine of 0 degrees is just equal to 0. That means that my total force is Kc q lambda times sine of 9.46 degrees over x naught I hat, or with the numbers all plugged in, 8.99 times 10 to the ninth Newton meters squared per Coulomb squared, times, and now I gotta go back up and remember what numbers we were using in the example. So lambda was 1.5 microcoulombs per centimeter, point charge was 2 microcoulombs. So I have 2.0 times 10 to the negative 6 coulombs for C. I have 1.5 times 10 to the negative 6 per centimeter, which is coulombs per centimeter, times 100 centimeters per meter, divided by 48 centimeters or 0.48 meters. And all of this is times sine 9.46 degrees I hat. So that all goes into the calculator. And what this ends up giving me is 9.23716 times 10 to the minus 3 newtons in the I hat direction, or if you'd prefer, this is 9.2 millinewtons in the I hat direction. All right, so that was a nice long extended example in terms of, well, an extended continuous point charge distribution. Oh, sorry, I say point charge. A continuous distribution of charges for an extended object. And so that is how much total force is now being applied to a point charge, including the direction. Other problems are basically similar to this one. It is mostly, as I've said here, the hard part, figuring out how to get dq, r hat, and r in terms of a common variable or set of variables. If it is a common set of variables, then that is going to imply more than one integration. So if you reduce it down to a, maybe q is in terms of dA, so it's like a distribution over a surface, then you're actually going to have two integrals, one for, let's say, x and one for y, or maybe one for theta and one for phi, something like that. If you have three variables, maybe you have a volume distribution, like a bulk distribution of charges, then everything should be in terms of, say, x, y, z, or r theta phi, or something like that, and you'll have a triple integral to do. But anyway, that is all for today's video. Hopefully you found this example interesting or helpful, and as always, thanks for watching.